All right, on Tuesday I made a video that apparently didn't have sound recorded with it. So I apologize for that. I did on today's module put a bunch of flipping physics videos that essentially cover the same topics with better visuals, obviously, than I gave you because he's got computer savvy that I don't have. So check those out if you want a little refresher. If you're at home, I do apologize for that, but watch those videos. You're also always encouraged to join my Zoom meetings and never do those. So, you can join Zoom meetings if you'd rather watch class as you would if you were here. All right, so on Tuesday, we introduced some concepts. We introduced the concept of torque. Torque is a force that either causes or could potentially cause some type of rotation. And the equation for torque, the symbol, is the lowercase tau, which looks kind of like that, depending on how you write it. You might see it written slightly differently. And it is not just a single number. It can be a single number, but you'd have to calculate it by multiplying the force that's creating the torque times the lever arm, the distance from the axis of rotation of the object to the point on the object on which the force is applied. Could be a capital R, lowercase r, it's just whatever you want. Times the sine of the angle between these two. These are vectors. Technically, torque is a vector. Technically, force and lever arm are vectors. So the angle theta is the angle between those two vectors. We don't deal in AP Physics 1 with the vector nature of torque. That is something that you'll learn when you take AP Physics C next year, which I've heard is not that many people. So hopefully more people sign up. There's a chance that it won't actually make next year. So any of you that are signed up to take AP Physics C, you might want to try to encourage some friends to do so as well. Tatum. I noticed you didn't sign up for Physics C. It's kind of upsetting. Just kidding. Okay, so that's the equation for torque. We also talked about rotational inertia. And we're going to kind of put that on the back burner for now. The symbol is I. For a point mass, it's mr squared. For extended objects of uniform density, there's different expressions for those moments of inertia or rotational inertias. And then we talked about Newton's laws for rotation. Okay. And we actually use Newton's second law to derive what the rotational inertia for a point mass was. And then I explained how you could take that concept and extend it using calculus, meaning you don't have to do it in this class, to determine what those equations are for rotational inertias for other objects, for extended objects they're called. Okay, so we use Newton's second law for that. But now we're going to kind of backpedal a little bit. We're going to backpedal a little bit like when we first talked about Newton's laws for translational motion, straight line motion. We just talked about, or we started by talking about systems in equilibrium. So that's what we're going to start with now. We're going to talk about systems in rotational equilibrium. And the easiest definition for equilibrium is, the easiest to remember is not accelerating. If an object is in equilibrium, it's not accelerating. If an object is in translational acceleration, if an object is in translational equilibrium, it is not accelerating translationally. If an object is in rotational equilibrium, it is not accelerating angularly. So translational equilibrium, it's not accelerating with that acceleration. Rotational equilibrium, it's not accelerating with that acceleration. Okay? So, for full-on equilibrium, like total equilibrium, both conditions must be satisfied. The net force on the object must be zero. If it's not, the object will necessarily accelerate translationally. But then the net torque must also be zero. If it is not, then the object must necessarily be accelerating angularly. So those are the two conditions. And you might ask, well, can one be zero and one not be zero? Or can the other one be zero and the other one not be zero? Yes. Yes, you can have a net force of zero and a non-zero net torque. You can have a net torque of zero, but a non-zero net force. That can happen. I'm going to show you some cases in which that can be true. But then you can have both. You know, obviously the net force on my coffee cup and the net torque on my coffee cup are both 0 because it's not rotating and it's not accelerating translationally. So yeah. And then you can have an object that is falling that maybe has a thruster on it that's causing it to accelerate angularly as it's falling. And then so you can have both. You can have neither. You can have one and not the other. You can have that other and not the one. Okay? And to kind of show you what I mean by that, or at least an easy way to see that, I got some simulations to show. Oh. That's the seesaw problem. We'll do that later. So here we're out in space. Way out into space. I got these two thrusters here. The top thruster is exerting a force of 5 newtons on this block. So it's creating a force of 5 newtons pointing down. And then this thruster on the bottom is exerting a 5 newton force, but it's pointing up, so it's exerting a 5 newton force pointing up. So what's the net force on this guy? 0. What do you think the net torque on this guy is? 0. So when I hit play, what do you expect to happen? Nothing. Exactly. Very good. Not very interesting, but this is a case where you have the net force 0 and the net torque 0. Now I'm going to keep those same two thrusters for every scenario here. I'm going to keep those same two thrusters, but I'm going to take this guy and I'm going to move him over to there. Okay. What's the net force? 0. Is the net torque now 0? No. Do you expect some rotation to happen here? Yes. Yeah. Do you expect some translational motion to happen here?
Yes.
A lot of people saying yes. Some people shaking their heads no. In order, and why do you say no, Alex?
Because if the force is 0 and the acceleration is 0, then it's not going to move translation.
Yeah, the net force is 0. The acceleration must be 0, so the object will not move translationally. In this configuration, it's a little counterintuitive, right? You feel like it should kind of move, right? But what Alex said is exactly true. When I hit play here, the net force is 0 because the two thrusters are constantly fighting each other, right? With exactly the same force. So even though you might intuitively feel like there should be some translational acceleration, there is not because the net force is 0. But the net torque is definitely not 0 because we see some acceleration. And in case you didn't catch it or you didn't pay it, I won't say pay attention, but if you forget your motion graph stuff applies to rotational kinematics as well. So if I wanted to graph angular velocity versus time, remember graphing velocity versus time? And measuring the slope of that tells you acceleration. If I graph angular velocity versus time and measure the slope of that, it also tells me acceleration. Notice it is using the standard coordinate axes that say that that clockwise rotation is negative. Counterclockwise rotation would be positive. So if I took this guy and put him over here instead, whoa. If I put it over here instead, I would expect positive angular acceleration. Okay. So this guy is creating torque now, right? Is this guy creating torque? No. And let me show you why. Mathematically. If this is our rotation axis, and it's not fixed to anything, it's just that's the center of mass of the object. This pointing towards the center of mass of the object is like pushing on a door hinge and expecting the door to open or close. It's not going to happen, right? But mathematically, and according to this equation, we can see it like this. I'm going to draw my lever arm for this force, right? I have a force. I'll call it Ft, the thrust force. The lever arm for that force is this vector. So the lever arm for that thrust force. Remember, vectors you can move around. So when you have two vectors that are pointing in the same direction, what's the angle between them? 180. 180. It could be 0 as well, right? If this thruster was pointing down, then the angle would be 0. But the sine of 0 and the sine of 180, you all should know if you're in pre-cal or calculus, is 0. So if I calculate the torque here, it's going to be the thruster force times the lever arm, which are neither one 0, right? They're both vectors that have magnitude. But then times the sine of, in this case, 180. The 180 degrees, the sine of 180 degrees is 0. Therefore, the torque due to this force is 0. So that force right there is not going to contribute in any way to the rotational acceleration of the object. This force, on the other hand, the force points down. So this thrust force points down. This thruster has a different lever arm, right? The lever arm is now going to be longer. You can do your, by geometry, this is a hypotenuse of this square, which is going to be longer than just the side. So that's the lever arm for this thruster. And then this is going to be the angle between them. And so to calculate the torque here, I would say, well, the torque here is going to be equal to that thrust force, the same one as this, times the lever arm for this guy, which is not the same one as that one, times the sine of this angle. That angle is not 0 or 180, so the sine of that angle is not 0. And so that I do get a net torque from that one, right? And because this torque wants to cause counterclockwise rotation, then I get a positive angular acceleration. Again, that's the convention. You can always choose whatever coordinate system you want. You can define clockwise rotation as being positive, but then you would have to also call counterclockwise negative rotation. So that's just like normal coordinate systems. You're free to define your own. You just got to be consistent with them. Okay. All right. So all that being the case, let's let this guy go for a minute. Not a minute, but long enough to get some graphs. So I get, in the slope here, I can determine the slope, which is the acceleration. This is, if you can't read it because you're far back, this is angular velocity versus time. Just like with normal velocity versus time, angular velocity versus time, the slope is angular acceleration. Now if I take this guy and move him over there, now he's doing kind of the same thing as this guy. He's creating, notice their forces are in opposite directions, but their torques are actually in the same direction. This guy wants to cause counterclockwise rotation. So does this guy. They both want to create counterclockwise rotation. And so those torques are going to add. And that's, again, this is the difficulty here, right? You can have different directed forces creating torques in the same direction. And so when I hit play, I've essentially doubled the torque, right? This guy had 0 torque. Now he's got the same torque as that guy. Same lever arm, same angle. And so I should get double the angular acceleration. Because Newton's second law for rotation says that Newton's laws for rotation, Newton's second law says that the net torque equals rotational inertia times angular acceleration. Well, the rotational inertia of the object doesn't change because it's the same object. So if I double the torque, I should get double the angular acceleration. And I can check that very easily by just noting the slope here. The slope of the bottom one, the first one, 0.073 radians per second squared. The slope of the top one, 0.146 radians per second squared, exactly double. Okay. So all of these situations I've shown you, the net force has been 0.
Wait, so Mr. Graham, I have a question.
Yeah.
So what if you had one of those forces like not going straight up, like against the other force? What if you had that crooked?
If you turned it a little bit?
Yeah.
Then you would have an angle that wouldn't be 0 or 180, right? You mean one of these two?
Yeah.
So if I take one of these guys and rotate it a little bit.
Wouldn't it then have tangential velocity?
Yeah.
Okay.
Yeah. And now you do have a net torque because you do have a lever arm, you do have a force, and now there's an angle between them that isn't 180, and for sure you would end up, it won't be a big angular acceleration.
Yeah.
And now notice it's also translationally accelerating. Because now the net force is not zero, right? That's a good question. And the motion would actually be kind of complicated. You'd probably make like kind of this kind of a path through space. Yeah. Good point. All right, aside from that, all of these situations had a net force of zero. Right? That last example had a net force that wasn't zero because we saw it translationally accelerate. But all of those had a net force of zero. Notice that if I take this one and put it... Well, if I take this one and put it here, and then take this one and put it up here, and I hit play, obviously it starts accelerating downward, but it's not angularly accelerating. And that's because the net torque is zero. The net force is not zero. The net force is not zero because we got two forces pushing down and nothing opposing them. So the net force can't be zero. But the center of the object, if the object is free to move, then the center of the object is generally considered its rotation axis. These guys have the same force, same lever arm, same angle between them, but one of them is trying to rotate it counterclockwise. One is trying to rotate it clockwise. And so they're creating opposing torques. So same direction force, but they're actually creating opposing torques. So the net torque here is zero, but the net force is not zero. Okay. And then again, as Jacob pointed out, if I just angle one of those, now the net force ain't zero, right? Now I have a force in the x direction that is not being opposed by any force in the y direction. I mean, in the negative x direction. And now the y component of this guy's force is not going to be as large as this one. So it should actually start accelerating to the right as well as down, and I should get a little bit of spinning. If we wait long enough, well, actually, yeah, now it's constantly redirecting, and so it's going to be really complicated. Let's see how complicated. Do I remember how to do this? Oh, it's not that complicated. It is wobbly, though. See it? I might have said this before. I remember specifically the reason I like doing stuff like that. I remember being challenged by my 8th grade science teacher to say if you were like looking down at the solar system, you know, as like from an aerial view of the solar system, and then you watch the Earth going around the sun like this, and then the moon going around the Earth, what shape would the moon's trajectory actually make as it goes through the solar system? And it's not as intuitive as you would think. Anyway, has nothing to do with what we're talking about now, but it's interesting to think about. Think about it. Okay. So, there is a new quest assignment, so you might see a couple of questions talking about equilibrium, both translational and angular, rotational equilibrium. So now we're going to talk about an example problem that's in the notes, example number 1. We're not going to talk about it directly first. We're going to first talk about the seesaw problem, and then that will extend to example 1 here, which is why I don't know why I turn off the light. Oh my gosh, too many things. We recording still? I hope so. All right. So a pretty common problem when you're learning about rotation is you got a seesaw, and I've created a base with a point on it, and then I've taken a plank of wood and put it so the center of mass of the plank of wood is right on top of the point, right? Otherwise known as a fulcrum. So if I hit play, it doesn't rotate. However, this is unstable equilibrium, as you might guess. So small variations in air pressure or just not placing it exactly right in the middle, they will dictate that equilibrium will not maintain itself for very long. So that's why it does end up rotating a little bit. That's like trying to balance like an egg on another egg, right? You can get it to happen, but a slight little nudge is going to make it so it falls apart. So that's unstable equilibrium. In general, there's two basic types of equilibrium, or at least as far as this. That would be like balancing a ball on top of something very round. That would be unstable equilibrium. Slight nudge, and it's going to fall off, and equilibrium gets de-established. Or in a valley, you nudge that guy, and it just goes right back into equilibrium. Right? That would be stable equilibrium. That would be unstable. So this is unstable equilibrium, just so you know. So it's not going to stay stable for very long. But then a kid comes along. So this is a seesaw. You guys know what those are? They probably don't have them anymore. Do they have them on playgrounds anymore? Because they're unsafe, maybe. I don't know. Who knows? Kid comes along, sits on the seesaw, and obviously it's not in equilibrium anymore. That kid is creating a net torque that's going to cause that to rotate. And has anyone ever actually played on a seesaw? Right? You want it so that you're balanced. Because if you're balanced, you barely have to push up at all in order for you to rotate up. And then the other person on the other side, they bend their knees and they stop them, and then they barely have to push up at all, and they go like that. If you're say me and my brother is a pretty stocky dude, he weighs a lot more than I do. If we're sitting on the same seesaw, equidistant from the center, whenever I'm down, he's up, he's creating more torque, right? And so he's going to move down a lot faster. And then he's going to have to push up harder in order to go back up, and then it's just going to go right back. And it's not as fun that way. You want it to be balanced. So if you have two people that are different weights and you want them to balance, they have to sit at different distances from the equilibrium point, from the axis of rotation. That makes sense, right? It should. That should be intuitive, kind of what I'm talking about. So if this is the kid, and the kid weighs significantly less than their mom, and this is mom comes along, what does mom want to do? Does she want to sit farther away? No, she wants to sit closer, right? If she sits at the same distance, which would be there, that's going to happen. And the kid gets launched into the air. And so what she needs to do is sit closer to the axis of rotation, and if she gets in just the right spot, then it's perfectly balanced, and that's where you want to be when you're playing on a seesaw. Not perfectly balanced, again, unstable equilibrium. Okay. So, a very typical problem is where does mom need to sit? Given the two masses, you know the mass of the kid, you know the mass of the mom, you know the mass of the plank that they're sitting on, and you know the kid sits a certain distance from the center of the seesaw. How far from the center of the seesaw must mom sit in order to balance the seesaw? And you cannot use Newton's laws for translational motion to answer that question. You cannot do it. Okay? You have to use Newton's laws for rotational motion in order to solve that problem. And the solution of this problem will actually explain something that you might have been told in middle school science, but might have wondered about if you're like me, and it wasn't until you learned physics that you're like, oh. So, first thing I'll point out is that above example 1, you have steps for solving static equilibrium problems. They can be summarized like this. First, you draw a picture of the object whose rotation you are interested in. So we're interested in the rotation of the seesaw itself. So you draw that object. When we did Newton's laws for translational motion, you could just draw a dot, or a small circle, or a small box, and connect all the forces to that. You can't do that with rotating systems because it's not just the forces that are important, it's where on the object those forces act that are important. So we have to go a little bit beyond just our normal free body diagrams. I'm drawing a free body diagram on this plank of wood, but I have to draw the object itself because the forces that are acting on it are all very important, but the positions of those forces on the object are also very important. All right, so the kid has a weight force that's bearing down on the plank of wood. Okay, I'm not drawing the free body diagram for the kid. I'm drawing the free body diagram for the plank of wood. When you are weighing yourself, you stand on your spring scale in your bathroom, and it tells you how much you weigh. How does it do that? Because your weight is pushing down on the scale. And its springs act in response, or digitally act in response to give you the reading of your weight. So this child is pushing down on the plank of wood, and we'll call that mcg, mass of the child times g. That's the weight force of the child acting on the seesaw. Let me draw my fulcrum. Sorry, guys. Forgot to do that. There's my base. And then I got mom, and I know mom needs to sit a little closer, but her weight is also bearing down on the seesaw. So mass of mom times g. Call these M1, M2, it doesn't matter. There's another weight force I need to incorporate. What's that weight force?
The weight force of the plank itself.
Yeah, the plank itself has weight. And so, and here's what, we had a nice discussion about this last period. MPG. We'll say MPG for M mass of the plank times G. We can draw, now that we have to draw extended objects, we can draw the weight force of that object, or we do draw the weight force of that object from the center of mass of the object. If it is a uniform object, that center of mass is at its geometric center. The center of mass is explained a little bit in the notes that I gave you. But we did have a discussion about this last period. Well, isn't there weight over here on the plank? Isn't there weight over here on the plank? Right? Isn't there weight forces due to all pieces of that plank? And the answer is yes, of course there is. But it turns out, and this is why we can't go too much farther, it turns out that when you know a little bit of calculus, you can actually break this, and I said similar things on Tuesday, you can actually break this plank up into an infinite number of infinitesimally small pieces of mass, each with its own infinitesimally small weight force. And when I add up all of those weight force vectors, those little tiny ones, then I get what is equivalent to the overall weight force vector for the entire plank of wood, which I can draw from its center of mass, its geometric center of mass. And those are not approximately equal, those are exactly equal. So at this point in AP Physics 1, you just got to take my word for it. You draw the weight force for extended objects from the centers of masses of those objects. Okay? And then you don't have to worry about anything else. You are able to do that because it's exactly like dealing with all the other stuff. But dealing with all the other stuff would be impossible. It would be way too time consuming. You wouldn't want to do it. Okay? You have a question?
Oh, yeah, I do. Will there ever be a time where the pivot and the thing holding it up, will there ever be a time where it's actually square instead of it being at one point it's at the entire top line of it?
Yeah. And maybe not so much in this class, but then you would have to use your noggin a little bit to see, well, because you know if this was a square base and you put mom here, it's probably going to rotate like that still, right? But then the axis of rotation would be on this corner of that square, right? Make sense?
Yeah.
That's a good question. Which kind of leads into something I'll talk about in just a minute. Anyway. So all that being said, to say the weight force of the plank I draw from the center of its mass. However, these aren't all the forces. If these were all the forces, what would the plank be doing? Yeah. With no other opposing force, the plank would be accelerating downward because I only have downward pointing vectors, the net force would not be zero. So if the plank is not accelerating downward, then that means I would have to have a normal force that's offsetting all of that. Right, that has to be exactly equal in magnitude to the sum of those three.
And that force normal is based on where the fulcrum is, right?
Yeah, it's where it's being supported. Mm-hmm. All right. So I've drawn my extended object. I've drawn all the forces. Now I need to draw the lever arms. This is something that we didn't do when we did Newton's laws for rotation. This is something that we need to do now that we're doing it this way, though, with rotation. So the lever arm for the child, which I'll call RC, is right here. The lever arm for mom, which I'll call Rm, is right there. What's the lever arm for the normal force? What's the numerical value for it? 0. What's the lever arm for the weight force of the plank? 0. So how much torque do you think the normal force and the weight force are creating? None. So I can say that. I can say that the torque from the normal force equals 0. I can also say that the torque from the weight force of the plank equals 0. So I like putting subscripts that indicate that. You can indicate those however you want, however is convenient. And so when I do my net torque equation, I can just forget about those guys. Okay? And again, why can I do that? Because the equation for torque is force times lever arm times the sine of the angle between them. If any of those things are 0, then the torque's going to be 0. Okay? Again, that's like trying to push down or push on the hinge of a door and get that door to open or close. It doesn't happen. You got a seesaw that's perfectly balanced. You push right down from the top at its center towards the fulcrum, towards the pivot point. It's not gonna rotate. Okay. All right. And since we're with our diagram here, so I've labeled all my lever arms, and then my angles. What's the angle between these two? In my drawing here, 90 degrees. What's the angle between these two? 90 degrees. A lot of rotation problems, the angle that you got to do the sine of in order to calculate torques is going to be 90 degrees. And as we all know, the sine of 90 degrees is 1. Just like the sine of 0, or not just like, but, and the sine of 0 or 180 is 0. Okay. And now, again, the question is usually like you have two masses. You got the kid that's got a certain mass. You got the mom that's got a certain mass. The kid sits a certain distance from the center. Where does mom need to sit? Right? How far from the center does mom need to sit in order to balance so that they can have fun on the seesaw? Well, to do that, I got to use Newton's laws. Right? And I could start with Newton's second law, net torque is rotational inertia times angular acceleration. We'll definitely be coming back to rotational inertia starting next week. But in this case, rotational inertia really doesn't matter because what's the angular acceleration that I want if they're going to be balanced?
0.
It's going to be 0. So we want the whole right side of this equation to be 0. Which means really we're dealing with Newton's first law for rotation, where the net torque is 0. So an object remains in constant velocity, or constant angular velocity in this case, constant angular velocity of 0 specifically in this case. We want that to happen, so the net torque must be 0. Okay. And again, we can ignore the torques from the normal force and from MPG because they don't create torque. There's no lever arm for those. So really I just have two forces creating torque. So the kid, in our standard coordinate axes, the kid creates what? Positive or negative torque? Positive. Now remember there's no rotation happening, but the kid's weight wants to cause positive rotation in the positive direction. Counterclockwise rotation. So we call that positive torque. So when I expand the net torque out, I have the torque from the kid, whose weight force is mcg, and that's positive. The mom, though, just like with the block and the two forces pointing down, they actually create opposing torques. The mom wants to create clockwise rotation, which is negative. And so we have a negative torque from the mom. Mass of the mom times G equals 0. Oh, I forgot one thing. It was because Gavin threw me off with that question. This is my axis of rotation, right? Right, the fulcrum right there. Remember, Gavin brought this up and it was like, okay, well, if it's on a box, you can still have rotation, but once it starts rotating, it's rotating about one of the corners, right? Depending on what is heavier and what has the larger lever arm. Interestingly, the axis of rotation is arbitrary. There's no actual rotation in the system. I could pick, this is my axis of rotation, the end. I could. And the physics will work out to give me the same results. Okay? I could pick this as my axis of rotation, and the physics would work out to give me the same results. It sounds strange, but it's true. It's just solving it that way would be far more cumbersome and far less convenient. So I like to think, I draw my free body diagram, I label my forces, my lever arms, and then I choose a convenient axis of rotation. Notice that this axis of rotation, the obvious one, is also the most convenient one. Because by choosing that axis of rotation, I've eliminated the torques due to two different forces. So I only have to worry about the torques created by these two forces. If I pick this as my axis of rotation, each one of these forces has a lever arm and has an angle that I have to incorporate. So I would have to have 4 torques here, and the geometry would be just a nightmare, and it would be ridiculous, especially since you can solve it in a much easier way. Now, you might be thinking, why is that even important? There are problems where it's not obvious where the axis of rotation will be. Okay. If you look at example 2 there, just look at that picture. Where's the axis of rotation? Right? It's not rotating. If you're an engineer designing something that's going to support a sign like that, then you got to make sure that it's not going to rotate. So where's the axis of rotation there? Don't know. Okay. So it's arbitrary. But if there's an obvious one, pick that as your axis of rotation. Measure your lever arms from there. Okay. Now the equation for torque, again, is mass. Not mass. The general equation for torque is force times lever arm times the sine of the angle between them. With both of these torques, we know that the sine of the angle is just going to give us 1. So we can just write force times lever arm. For the child, it's going to be the mass of the child times g, that's the force, times the lever arm for the child, minus the mass of the mom times g times the lever arm for the mom, and that's going to equal 0. Again, the sine of the angle for both of those torques is just 1, because the angle itself is 90 degrees in both of those cases. There's a simplification I can make here. What's that? Everyone brought gravity to the party. And so this simplifies even further to something that's mathematically pretty easy. Mass of the kid's lever arm, minus mass of the mom, times mom's lever arm, equals 0. A couple ways we can write this. We can add rm to both sides and get that the mass of the child times lever arm for the child equals the mass of the mom times lever arm for the mom. I can write this as a proportion, 2 ratios, right? I can say the ratio of the mass of the child to the mass of the mom, right? If I divide both sides by mass of the mom and then divide both sides by lever arm for the child, is equal to the ratio of the lever arm of the mom to the lever arm of the child. Looking at it that way makes it relatively clear that, well, the one with the larger mass has to have the smaller lever arm. Right, for those 2 ratios to be equal. Interestingly, though, and this is what I kind of alluded to earlier, G canceled. That's important. That's important. I'm assuming everyone in here eats their veggies. Veggies, fruits, and veggies. You don't eat fast food a lot because that's poison. But when you go and you buy your produce, you put it on a scale here. If you got a recipe that calls for something, you got to have a certain amount of it. You put it on your produce scale. Now this one is in a physics department, so it's converted to read in newtons. But if I measure something as 4 newtons here and I take this to the moon, it's just a spring scale. Is it going to read 4 newtons on the moon? No. Because it's a spring scale. It works like the ones in the produce section in your grocery store. The weight force is what dictates what the reading is going to be. Okay, so this measures weight. You take it to the moon, you take it to Mars, and it's going to give you different values because how it measures stuff, it measures how hard gravity is pulling down on the object that it's connected to. Okay, but then you might have learned it. You might have heard this in middle school, and I literally remember this. Why? Both of these things measure the weights of objects, don't they? Or at least they can be calibrated to do so. Both of these things can measure things that measure the masses of objects, right? But you're told that while this measures weight, right? The spring scale in the produce department at your grocery store measures weight. The triple beam balance measures what? measures mass. If you weigh an object, weigh in quotes, meaning measure the mass of an object here on the Earth with this triple beam balance, and then you take it to the moon and do it again, then you get the same reading. You take it to Mars, you get the same reading. And that's because the triple beam balance works like the seesaw. You got a rotation axis right here, right? And you put something on this, and then you move this around until it's balanced, just like Mom moves herself around until it's balanced. And then once it's balanced, the torques are balanced. When the torques are balanced, then the G's cancel out of the equation. And so the value of G doesn't matter, which then allows you to, based on the distances, which are calibrated with the values on the little thingy, allows you to calculate or measure directly the masses of objects on a triple beam balance. So triple beam balance, the produce scales just use the pull of gravity to measure the weight of an object. A triple beam balance balances the torques created by two different objects, or three or four, depending on if you're using all the little slider guys. The triple beam balance balances torques. And when it balances torques, the value of G cancels out. And so that's why triple beam balances measure masses, and the produce scale measures weight. All right. Which brings us to example 1, which we'll get started on. And this used to be, years and years ago, I don't know if you remember a time before COVID, but years ago, we used to do labs in physics. And this is one of the labs that we did when we learned about torque, when we learned about balance torques and Newton's laws for rotation. We would give our students a meter stick and a couple of masses that were known, that had the masses stamped on them. We'd give them an unknown mass. We'd give them a way to hang the masses on the thing and a stand that they could balance the meter stick on. And then we'd give them an unknown mass, and then they'd have to determine using torques and measurements what the mass of the unknown mass was and what the mass of the meter stick was. And if you did that lab carefully and you made your measurements carefully, you could actually get to within 1% or 2% of the actual value. Okay, so, and you would go through a process very similar to this example problem. 10:08, right? You know we're going to be kept in here for a few minutes after, right? Just so you guys know. That's what that announcement last period was for. So yeah. So we probably won't get to the end of this, but we're going to get it started. The uniform meter stick has an object with a mass 800 grams hanging from this 15 centimeter mark, and an object with mass 350 grams at the 70 centimeter mark. It balances horizontally on a pivot placed at the 35 centimeter mark. What is the mass of the meter stick? So again, this is kind of like the lab that we did. It's almost identical to the lab that we used to do in this class when we were first investigating these concepts. So here I got my meter stick. And I'm going to have I'll call it mass 1. It's going to be at the 15 centimeter mark, so about there. So that's going to be M1G. Then I have at the 70 centimeter mark, which is probably like right about here, M2G, and that one's smaller. At the 50 centimeter mark, that's where we draw the weight force for the meter stick itself. So I'll call that, right from the center, I'll call that mass of the stick times G, MSG. And I know that the pivot point is at the 35 centimeter mark, so we'll just say it's right about there. And that's where we get the normal force that balances the translational weight forces, creating translational equilibrium. So there's my free body diagram. I'm going to identify my axis of rotation, the convenient one, the obvious one, axis of rotation. But now I got 3 forces that are creating torque. So I got 3 lever arms. So I'm going to call this R1. I'm going to call this RS, lever arm for the meter stick. And then this will be R2, lever arm for mass 2. Okay. Notice again, all angles are 90 degrees. So the sines of all the angles are going to be 1. Now, you got to be careful with this kind of a problem, though, because M1 we're given 800 grams, but we're not going to use 800. We're going to use 0.8 kilograms. M2, 350 grams, or 0.35 grams. Again, you're not going to leave right when the bell rings, just so you know, so you don't need to start packing up now. We're not going to finish this problem, don't worry. And then lever arm 1. What's lever arm 1, guys?
Oh, 25, or, you want to be 25?
Not 25. It's from 15 to 35. 20 centimeters, right?
Hold in your classroom and clear the halls.
Wait, what is this one?
It's like if there's a fire, but it's not bad enough that we need to leave or something. I don't know.
Is this the drill?
This is a drill.
Shelter in place.
It's not shelter in place because they say to go about
Hold
your
in your
business.
classroom and clear the halls.
So what's R2? Notice I converted it to meters. 35. 35 centimeters or 0.35 meters.
Hold in your classroom and clear the halls.
And what's the lever arm for the weight force of the meter stick?
It's 0.15, right?
0.15, good. And then so all that, and then the mass of the meter stick would be our unknown. And we'll go ahead and cut it there.
Hold in your classroom and clear the halls.
The quest assignment is available. The first few questions definitely we covered today, so you might want to get started on that. If you're at home, you definitely want to get started on that for today's attendance. Yeah, hopefully this recorded and you hear sound on this one.